All right. Hey, AP Chem students. Today we start Unit 3, which is all about intermolecular forces and properties. It kind of jumps all over the place. So we're going to start with intermolecular forces. Intermolecular forces are abbreviated IMFs for short. So when we talk about IMFs, we might want to, or when we talk about intermolecular forces, we might want to be ready to use that abbreviation. So IMFs are basically forces between atoms. So we're talking about being between atoms. So this could be within the same substance. Like if we have a whole bunch of water, like a collection of water, we could be talking about that attractive force, or we could be talking about the attractive forces between two separate substances, such as maybe water and salt. This would be an ion dipole, but we'll get to that part for just a couple of seconds. So why do we care about these intermolecular forces? Well, these intermolecular forces depending on their strength, they tell us a lot about, sorry, I'll erase that. Depending on strength, all right, they tell us a lot about like what phase or state of matter the substance is going to be in. All right, so they tell us about boiling point. They tell us about melting point. They tell us about vapor pressure. There's just a lot of things that these intermolecular forces tell us about the substance. And so thus we need to spend some time kind of learning about them. All right, so we're going to actually start with the weakest and work to the strongest intermolecular forces. But again, this is all relative, right? Dispersion forces can actually be quite strong if you have a ton of electrons. So we'll kind of just jump in there. So our types of intermolecular forces, our first type is called a dispersion force, also known as a London dispersion force. All right, they've actually went to dispersion recently. Just dispersion, not London. So what happens here is this is based on kind of like a simultaneous or an instantaneous. This is an instantaneous dipole being formed. All right, and what's happening there is, if you think about it, our electrons are in the electron cloud, right? Kind of like we have in this handy-dandy picture on the left, right? We have our electrons in the cloud, but they're not always going to be an equidistance apart from each other. So sometimes they're going to all kind of be bunched up on one side, and that would create a slight negative. That's the lowercase delta, all right? But that creates a slight negative and a slight positive, thus this is an instantaneous dipole right here. All right. And so what we're talking about is just a very slight instance where this all occurs, but it does actually create some attraction between the molecules. All right. So a big thing that this depends on is our number of electrons. All right, the more electrons we have, the better chance that we have of forming this instantaneous dipole. And then the stronger that attraction is, right, within those molecules or between those molecules. The other thing is we could also be talking about like the length of a substance, right? Or how kind of like long and drawn out it is. If we have a long carbon chain, like octane, where it's like 8 C's, right? That's 5, 6, 7, 8. So this is octane, and then there's hydrogens all over here, right? Each of these dashes is a hydrogen. So what we have there is now we have like this big giant kind of area that these electrons can all gather. They could technically all gather right over here. This would be a very large dipole, even though it would be instantaneous. They could technically be all over there at some point. That could be a pretty large dipole. So our dispersion force would actually be pretty strong right there as far as attracting other positives, since that would be a slight negative. Okay? The other key word here is called polarizability. Polarizability is just based on number of electrons. All right. Again, this is based on number of electrons. And it's like, if you think about it, it's about the ability to create poles. All right. So we're talking about the ability to create like poles, and we're talking about dipoles. All right. Now our next one So that was our first force. That is present. This one is present in all molecules or in all substances, right? Because everything has electrons. So this is all substances here. Now, if we go to dipole-dipole, this is only present in polar molecules. This is only present in polar molecules. All right? So dipole-dipole forces this is where we truly have a dipole formed. All right? So we have an attraction between two poles or two dipoles. So we have a slight negative and a slight positive form. So if we look at like HF, right, just for an example, we have HF, right? We know that to be a polar molecule. We know F has like a slight negative on it. If we draw that, ooh, I erased a lot. Okay, so there's HF. We have this slight negative here on this side because the F has a higher electronegativity, right? And then we have a slight positive on this side, which means we're creating a pretty large dipole where all the electrons are kind of chilling over here with the F, right? And so it's going to be attracted to other positives or slight positives, such as, like, maybe if we have HF, it would be attracted there, right? Because the H is slightly positive, and so it's going to be attracted, and it's going to line up like that. So this depends on the polarity, right, of the substance. Okay? And the polarity depends on the difference in electronegativity. And if we think about electronegativity, remember, as a review, fluorine is our most electronegative element. So kind of like their distance apart on the periodic table will tell us about our dipole-dipole force. Okay? Our next one kind of goes along with that, but this is like in a mixture for sure, right? This definitely has to happen in a mixture. Those other two could have been like pure substances where there's not a mixture, but this one has to happen in a mixture. And this is where we have an ion dipole force. This is usually occurring between like an ionic compound and water, right? When we dissolve an ionic compound in water, we have these ion dipole attractions. So let's think about it in terms of like when I put table salt in water. So if I drop table salt in water, I get these Na pluses and these Cl minuses, right? And so for the Cl's, I'm going to have H's attracted to the Cl portion. And for the Na, sorry, I blew that up just a little bit, I'm going to have O's attracted to the Na portion because the O is a slight negative because it's a little bit more electronegativity, right? Or electronegative than the hydrogen. So it's got that slight negative. And so they gather up and they actually kind of line up like that. Okay? And so again, this depends on the polarity of a substance. All right? So we've gotten through 3. There's one last one, and we have hydrogen bonding. Hydrogen bonding is the strongest of the intermolecular forces, right? So this is our strongest. And the really big key here is that it's not truly bonding. Not truly bonding. All right? Even though it's called a bond, it is not a bond. But what has happened here is we have hydrogen bonded to one of the 3 bigs, if you will, F, O, or N. When hydrogen is bonded to fluorine, oxygen, or nitrogen, this creates a very, very polar bond. So what hydrogen bonding is, it is truly just like a really, really strong dipole-dipole force. All right? And how they figured this out, and it goes into detail in our book, but how they figured this out is what they look at like the boiling points of like water, and let's look at something like, so H2S, right? H2S, not that you guys know this, but H2S in its natural state is a gas. All right? H2SE, also a gas. Most nonmetals, most covalent compounds are gases at room temperature because of the lack of intermolecular forces. But if we look at water, H2O, whoops, that's not an O. All right, if we look at water, we have H2O, and it is a liquid at room temperature, right? And so they had to figure out a way with this, and what they realized is that the bond in water, the OH bond, is so polar that it creates almost like it's an ionic compound, and it creates that great attraction between other atoms, right? And so here's my H, right? It's going to have other O's attracted to it, right? And it actually is very rigid, and kind of also, that's also why ice forms that rigid thing. But yeah, this is something very big, all right? And this is what we got going on. And this is why water, like you can bend water, or water on top of a penny if you put in drops of a penny, or you can form it like fill up a water bottle too much and it's got that kind of bubble on top, if you will. All right. So that's what we've got going. And so those are our intermolecular forces. I encourage you to read through this quick summary because that'll help you, but that's the big parts. Okay. See you next time.